Oh, and we're good.
I feel like I'm playing Mario.
I know, it kind of feels like that, right?
You gotta hit the gas pedal right forward.
So guys, this is where I wanted to start. As I told you when I saw you on Thursday, Thursday, the new version of the book got rid of some very fundamental questions, and there was no way that I could recover. There weren't replacements that were even close. And guys, maybe if you even looked at the questions on potential energy in the book, they weren't assigned to you, but did any of you happen to glance at them? It's really interesting. All of the potential energy questions in the book were actually having you think about quantifying the potential energy based upon attractive forces between dislike charges. And it was all math. And I was like, that's not math you need to know on the AP. Anyway, it was a mess. So, guys, what I ended up doing was just retyping all the questions. I know I told you about this. But, guys, I'm going to need you on this one. If I made mistakes in what I wrote, if the answers, please, and you guys are good about this, help me match these up because I did my best, but I'm sure that I missed things. Guys, notice that 3 and 4 were out of our book. And then the remainder of them were not. So I'm going to leave this open just because I suspect I'm going to need to do some editing. But then, guys, with that said, these were, I believe, the answers. So let's make this about you getting your chemistry questions answered. But at the same time, if you can help me doctor up the solutions or the questions, let me know. Yeah.
I didn't know where to find the questions because you told us we were going to do different questions.
Yeah. I don't know if you've made this connection, but the idea is that we always have slides, right? And guys, this is really for all of you. We always have slides in class, but those slides are always posted on our website. So if you had gone to the energy intro day and then gone to slides, you would go to the very last slide, and here's all those questions. Does that make sense? Okay. Regan, go ahead.
So I was a little bit confused on question 4 for part C.
Hold on. So that's a book question, right?
Yeah.
Okay, hold on. Let me put this up. And so this is a chemistry question, right? And not a what did you type question?
Oh, yeah.
Okay, so hold on. Okay, I'm caught up. Go ahead.
So based on the model, I'm just confused for C where it says how do you find, how can you tell which one the experience is in that?
Okay, so look, guys, let me just tell you right now. What you're going to see, and guys, this will be helpful for you to understand. What you're going to see is in the next couple days, there's information that we are going to be digging into. But guys, what you're going to see is that unlike other days in here, where it's like yesterday and today and tomorrow, guys, for the next few days, it's going to be kind of already talked about this. Let's maybe talk about it again, and then maybe... So you're going to see a lot of mishmash amongst this material. And guys, sometimes that's confusing to people because they're like, wait, I thought I learned this. Did I miss something? Because you're used to that. And guys, the answer is you haven't missed anything. There is a mishmash. So Regan, with that said, looking at question number 4, it's going to be up in the slides. We are going to talk in more depth about those pictures in number 4 in a few minutes. But let's talk about it. So, guys, you all got your books open, right? Page 202, we're looking at question number 4, and it says this. The contents of the closed box in each of the following illustrations represents a system. Guys, system is something that you can't just read through and go, oh, I've heard of that before. Guys, the system is the part of the universe that we are studying. So if that's the system, what's everything else? Surroundings. Good. Now read on and it says this. And the arrows represent the changes to the system during some process. And then the length of the arrows represents magnitude. So guys, let's remind ourselves. We've got the system, we've got the surroundings. But guys, if we want to change, just like our metal block, right? If we want to change the energy of our system, be it the block or the box, guys, there's only two ways to get energy in and out of a system. What are they? Heat and work, and that's it. Good? Okay, now let's read on. And it says this. Which of these processes is endothermic? Now, guys, that was drawing on something we haven't talked about yet. But I thought it was a fair review question because we talked about it last year, and we're going to get into it a lot more today. But with that said, when we hear thermic, are we thinking work or heat? Heat, right? And endo means into what? Into the system. So we are looking for Q arrows that are going in. And that would only be, let's just call it 3, triple I. Is that okay? Okay. Then B, which is, Regan, right, the question you wanted to talk about?
C.
Oh, C. Well, let's keep going. So B, which of these processes, if any, is delta E less than 0? Now, guys, think about what that means. If delta E is less than 0, it is negative. But be careful. It's not just thermic. It could also be work. But what we know, think about this, if delta E is less than 0, net energy is going out. So that means the outs have got to be bigger than the ins. So I would say letter I does not qualify because the work arrow going in is bigger. Letter number 2, that's not even an option. And letter 3 looks like to me, so is it none of them?
None of them.
Hey, there we go. All right. And then letter C says this, for which process, if any, does the system experience a net gain in internal energy? So guys, what we're looking for there is a bigger in than an out. So I would say the easy one is the middle one, double I, that's only in. I would say triple I would qualify because the in heat is bigger than the out work. And then guys, I would say single I qualifies as well because the in work is bigger than the out heat. So I would say all 3. Did I get it right?
Yeah.
Hey, really? Oh, that's not the right question. Never mind. So, Regan, what was it making sense?
Well, I was just like confused with like how you like just determine like the net gain. Like if you just like look at the arrows, or you just have to like.
But do you see it now that and it was sort of hidden in the question that the length of the arrow represents magnitude?
Yeah.
Is that okay?
Yeah.
Okay. Guys, what else? Questions on the homework, please.
You've missed an E in therefore.
You can actually spell it both.
You can?
That doesn't come up on spell check.
Really?
Yeah. The book of Romans just took on a whole new...
Evil.
You guys have noticed that, right? Like every single chapter in Romans starts with therefore. Paul is a master of argument. Guys, what else? Are we done? I love being done. Okay, so this is where I'm going to need your help. Oh, well, actually, wait. Anything weird about the questions or the answers and how they interrelated? So I can use this next year and it's going to be okay? All right. So, guys, with that said, FERPA is about to rear its ugly head. You guys know about FERPA, right? The Federal Educational Right to Privacy Act, which means as soon as you turn 18, your parents can't see your grades. Yeah. Actually, wait, it's 19. Yeah, but you understand that this is a saving piece of legislation for college professors. Because increasingly now college professors have parents of college students calling to argue their grades for their kids. College, right? Yeah, let go. But parents can't talk to, or I'm sorry, the professors can't talk to parents because FERPA says that is no longer legal because your children are emancipated when they hit 19. So all of that to say, guys, when I go to record homework, what I need you to do is remind me to pause the video, zoom this.
I can just imagine if that happens.
Oh, it happens a lot, and we're like, oh wait, we don't have a screencast. Okay, guys. This is what we're up to today. First law of thermochemistry and enthalpy.
This seems exciting.
I've heard of entropy.
I've heard of enthalpy many times when I was doing my summary. Every single chapter is like enthalpy.
The enthalpy of the system.
Also, he is a random
Like,
graph
oh,
paper.
great.
So guys, this comes with a couple caveats. First caveat is this. Do not Google the first law of thermodynamics. Guys, if you look, because we're all going to go to Wikipedia, right? So guys, if you start to do a deeper dive on the first law of thermo, you're going to find stuff online that at the surface even seems to contradict what you're learning. It is not contradictory. Guys, understand that my job as your Gen Chem teacher for college is to make this accessible. So what you are getting is a distillation of the first law of thermo. We're going to make it just as deep as it needs to be to serve our purposes. But guys, if you get into engineering or if you get into chemistry as a profession, there are all sorts of interesting implications and connections that we don't need to talk about. Then guys, number 2, enthalpy. My guess, just a guess, but guys, my guess is on your 4-quadrant thing, down in, was it the bottom right corner where you wrote questions?
Bottom left.
Bottom left. I'm guessing a fair number of you have the word enthalpy down in that corner. Okay, so guys, here's the deal. This is where I earn this is where I earn my living. Guys, you're going to find that enthalpy is actually deceptively simple. So I know that there are a lot of questions about it, but guys, let me take a swing at this, and there's this moment where we're going to introduce the idea of enthalpy, and you're going to go, really? That's it? And the answer is going to be, yeah, really, that's it. So guys, we'll get there in a minute, but for now, what we need to do is we need to go back and review, and I'm realizing I need some writing tools, so let me grab those. And then we'll get going. Here we go. So, guys, whether you choose to draw this or not, this is actually question 4 in a nutshell, the thing that Regan brought our attention to. If you want to draw it, that's fine. If you don't, that's fine too. But guys, you should be able to agree to everything that's about to come up on the screen. If you can't, ask questions. So guys, here's where we are by review. Here's our system. And guys, we understand that our system is that portion of the universe that we are choosing to study. At that point, guys, everything becomes around it, becomes the surroundings. Now, guys, what we learned is that this system has what we call internal energy. And guys, what are the 2 kinds of energy that a system can have? Kinetic, not heat and work. That's how it changes. Guys, it is kinetic
And potential.
or potential energy. But now, guys, this. Those can interconvert. This is where we come back to our block. And guys, remember the idea is that we had our metal block here, and we said that this had neither kinetic nor potential energy. Then I did some work, and now it has potential energy. But guys, as it falls, what's happening to its amount of potential energy? Going down. Kinetic is going up. That's the interconversion, but what is still the total internal energy of the block? The same, excluding air friction. So guys, these can interconvert with no net loss in energy. So now, how does energy get in and out? And there, guys, the answer is work and heat. So guys, energy can get in and out of the system via the paths of work and heat. You guys okay with all of that? Okay, so in summary, energy within a system can go between potential or kinetic or vice versa with no net change. In order to change the energy of a system, then guys, we've got to have the system interacting with the surroundings, and that can only happen through work or heat. Guys, anything there you want to talk about? You ready? You good? Okay, first law of thermo, you ready? So guys, you are about to become accountants.
Oh, great.
Oh, I know.
My dream job.
No.
Almost as bad as lawyers.
Oh, guys, it's awful. Like, I'm good. like pretty darn good with numbers, but if you put dollar signs in front of them, my brain explodes. Seriously, like I hate to budget, I hate to track my family's investments. My wife loves it. We're a great pair. I hate it. So accounting to me is like death. But guys, accounting in chemistry is actually something we all need to get good at. And guys, these are the rules. First law of Thermo. And the first law of Thermo simply says this: energy is neither created nor destroyed when changing forms or transferring between the system and the surroundings. Guys, some of you right now, your ears are tickling a little bit. But before we talk about the tickle, we've got to bring this to bear on the diagram that we looked at previously. Maybe something worth writing down.
I have a feeling this is important.
Perhaps. Yeah.
No, I don't think this will be on the test.
No. All right, guys, let's chat. Let's bring this all together. Here we go. Changing forms. What are our options there? What are the forms of energy? Kinetic and potential. So guys, we have energy, kinetic, and we have that inner conversion between energy, potential, and we've already established the idea that these can interconvert with no net loss in energy. But then guys, we've got this idea of transferring between system and surrounding. How does that happen? Work and heat. So Q is heat, W is work, and guys, that's it. That is our exhaustive list. So guys, basically the first law of Thermo just brings together the things that we established on the previous slide. But guys, when you think about the definition written out of the first law of Thermo, some of you might have been thinking, wait a minute, I've heard of this before.
Sounds a lot like the law of conservation.
Sounds a lot like the law of conservation of mass. And guys, we actually call it, some people will call it, the law of conservation of energy. And guys, at the end of the day, simply what it's saying is that energy is conserved. It is never created or destroyed. Let me go first. You guys okay? Is this sitting okay? So guys, there is one conversation that we can have as a result of this. We're not going to do a deep dive on it. But guys, now we have the law of conservation of mass. Matter is never created or destroyed. We have the law of conservation of energy. Energy is never created or destroyed. But guys, do you understand this? The amount of energy in the universe is always changing. And the amount of mass in the universe is always changing.
E equals mc squared.
And that's the relationship.
Thank you, Einstein.
Thank you, Einstein.
Don't think Einstein.
So, guys, in the mind of a physicist, matter is just condensed energy. And so, guys, energy can convert to matter, and matter can convert to energy. So really, the conservation is not just energy, and it's not just matter, because energy can be going up and down, but as energy goes up and down, mass goes up and down, matter goes up and down. And so really, the thing that is overall conserved is the total amount of matter and energy added together. So Big Bang, however this all got here, guys, there's a finite amount of matter and energy in the universe. Matter is conserved in chemical processes. Energy is conserved through work and heat and the interplay of kinetic and potential energy. But matter can become energy, and energy can become matter through nuclear processes.
We just won't ever do that, so we don't have to do that.
Not in here.
That's what you think.
That's what you think.
That's actually our last lab.
That's our last lab.
An unregulated nuclear reactor.
That's right. That's right.
We get to make a nuclear reactor.
Now we're gonna
You know, it's actually interesting. One year we actually went up and saw the you guys know the U has a breeder reactor, and we actually got to go up and see it. It was pretty cool.
We should go on a field trip.
We maybe at the end of the year if you guys want to pull it together.
Yeah, let's do it.
All right. So guys, with this said, and again, I told you mishmash, right? Kind of back and forth. Guys, this is where the mishmash begins. So guys, we need to now come back to the idea of internal energy. And Sharp got us thinking about this. Shoot, maybe it was just a casual conversation. I'm not sure. But guys, we're going to get into something a little bit interesting here. And maybe Sharp, you'll pick up on this, and if you want to dig deeper, we can. So guys, when we talk about the energy of the system, we've got to consider all of the sources within the system, and we call that internal energy, and it's abbreviated E. So guys, the abbreviation E refers to the total internal energy of a system. I wonder if they took this equation out. Yeah, but it's really not an equation anyway. So guys, E is the sum of all the kinetic and potential energy of a system. And again, I know that this we've talked about before, but we need to bring it back in front of us because guys, there's something interesting that you need to know about this idea. So total internal energy is the sum, it's abbreviated E, it's the sum of the kinetic and potential. If you want it as an equation, we can do this. But guys, this is the thing that's weird. I'm going to throw this out into the room and then I'm just going to let you chew on it for a minute. Because you can't measure E. Wasn't it you, Sharp, that brought up this conversation? And we talked about state functions for a second and I said we're going to skip it? Yeah. Guys, you can't measure E. You can't measure the internal energy of a system. It's unmeasurable. But we can still figure out what it is. So now you're going, wait a minute. If I can't shove an energy meter into a block and figure out how much energy it has, then how can we measure energy? And guys, the answer is indirectly. Let me give you a strange analogy, but it actually works. So guys, we are starting at some level to understand what black holes look like. We've actually taken a picture of a black hole, and if you haven't seen the video, it's fascinating to think about what these things look like. But guys, we're actually not taking a picture of the black hole because light can't get out of a black hole, so we can't see the black hole. So what are we actually seeing when we find a black hole?
The accretion disk.
That's true, but keep going again. What? Kind of, a little closer.
The absence of the light?
Yeah, so, and even a little, but what we're seeing, guys, and how do you know accretion disk?
I am significantly too obsessed with how black holes work.
I love this. And we won't get into exactly what an accretion disk is. But guys, basically what we're seeing is we're seeing the black hole suck all of its neighbors in. And as this black hole is drawing in matter from all the stars and the gas clouds around it, guys, what we're actually doing is we're not looking at the black hole itself, we're looking at how the black hole affects the things around it. Does that make sense? That's the same way that we measure energy. So guys, let that sink in. So we can't measure energy directly, but what we can do is we can measure how the system is affecting its surroundings. But now guys, bring that thought full circle. How does the system interact with its surroundings? How does a system interact with its surroundings? That's it. Work and heat. And guys, if a system interacts with its surroundings by heat, what are we going to see happening in the surroundings?
The temperature.
Temperature changes. And what if the system interacts with the surroundings through work? What are we going to see? We're going to see things move around. And so guys, that is actually, and again, when you get into the book, and you've already been through it, you read about state functions. Guys, there are university professors that would tell me I'm making a really big mistake right now, but I'm not. I know it to be true. Guys, we don't have to talk about this through the lens of state functions to understand it. We'll let you get deep into that in college. Guys, what you need to understand right now at some level is you can't measure the energy of a block. But what you can do is measure how the block interacting with the surroundings changes the temperature or the position of the surroundings, and we can measure that. And from that, we can figure out the energy of the block. So guys, it goes like, oh, I'm still in drawing mode. So guys, it goes like this. Let me get rid of this. Let me hop back here. So guys, fundamentally, the idea is this. We cannot speak of this. And guys, the word that we use is empirically. Remember when we said empirical formulas does not mean simplified formulas? Guys, do you remember what does empirical mean? Directly measured with collected data. Guys, empirical means based on experimental data. And so guys, we can't measure the energy of a system. What we can do is discuss energy changes and then talk about how the energy of the system has either risen or fallen based upon its interaction with the surroundings. Guys, this is going to be critical on Wednesday, but for now, we're going to simply talk about it this way. We're going to talk about changes in energy. And guys, like any other change, it's final minus initial. And guys, we got to drive this home because this is not a relationship that they gave you on the equation sheet, but we need to talk. Got it all down? So guys, it goes like this. Why is it important that you understand this equation properly? So, as an example, guys, you know that I had a weird year a couple of years ago. I haven't been able to train real hard. I'm starting to get back into it. But guys, right now I'm 25 pounds above my race weight. I like to race at about 175 pounds, and right now I'm 200. So, imagine that I come back in the spring and I've gone from 200 down to 175. How much weight have I lost? 25 pounds. But now guys, plug that into this equation. What is my final weight? 175. What's my initial weight? 200. So when you do the math, what do you get? Negative 25. What does the negative tell you? Lost. Guys, that is important. When you do these calculations, it's got to be final minus initial because that negative sign tells us direction, which we're going to tie to endo and exothermic in about 2 minutes. So guys, when you do changes in energy, it's final minus initial. So guys, what about this? What if the change in energy, think about this. So guys, what if the change in energy is negative? Did the energy of the system go up or down? Down. And what if it's positive? Why not? So guys, if final is bigger than initial, then the change in energy is positive. And if final is smaller, then it's negative. So guys, the bottom line here is signs are critical. Remember I told you you're going to be fighting over your lab data in a couple weeks? About 10 days? Guys, this is going to be one of the things that takes you down. You're going to get your signs wrong. It's important. Careful. I know, but that's not okay. Okay, you guys sitting all right? Okay, now guys, I wonder if you're capable of going to this place. So guys, we now understand that signs are important, right? our negatives and our positives are important. Because I have a question for you that I don't even want you to talk about. But I want you to think through this. Guys, when we say positive and negative, and please don't just, are we talking about the system or the surroundings? Now let's look. So when we say positive or negative, are we talking about the system or the surroundings? And guys, if the answer to that question seems easy, it's because you haven't taken physics. Because the answer in physics is the opposite. So let's look at it. So guys, coming back to our picture, right? Here's our system. What's all around it? Surroundings. What's inside it?
Energy.
Internal energy. How do we get the internal energy to go up or down? Work or heat. So guys, the trick is this. You are in the system. So guys, our system is our frame of reference. In physics, it's backwards. But in chemistry, our frame of reference is in the system. So guys, when we talk about this idea that energy change is positive or energy change is negative, guys, the idea is it's positive or negative relative to the system. Is that okay? And we will always place our frame of reference in the system. But now, guys, what about this? What if we shift our frame of reference and we put ourselves in the surroundings? What changes?
Everything's
The
backwards.
signs.
The signs all change. But guys, what about the values of the numbers?
No.
Says who?
Law of conservation of energy.
First law of thermodynamics. So guys, and this is again going to be something tricky when we get into lab on Wednesday. Guys, we are going to carry out chemical reactions. And we can't measure the energy of those chemical reactions. We've already established that. So what can we measure? How these reactions interact with the surroundings. And they are going to do this through the avenue of heat. But now, and temperature, we'll measure temperature. So guys, if this reaction causes the temperature of the surroundings to go up, did the system gain or lose energy? Let's say that again. If a chemical reaction causes the temperature of the surroundings to go up, did the system gain or lose energy? It lost energy. And guys, this is where you're going to get so tangled up in these signs that you've got to fundamentally understand this at a logical level. So guys, the idea is that if we are in the system, and if that system causes the energy of the surroundings to go up, like heating it up, temperature goes up. Guys, if the temperature of the surroundings goes up, the energy change is negative because the system is losing energy to the surroundings. Chew on that for a minute, y'all. That's important. In order to measure energy changes, we are going to observe the surroundings, and from that we can intuit what's happening to the system. We are always then in the system, so if energy goes up, temperature in the case of the lab, then the energy of our system is going down. Guys, thoughts or questions about that important idea? Please.
I'm kind of confused what it means when we're in the system.
Yeah, so the idea is it's helpful for us to have a frame of reference.
Oh, okay.
So imagine this. So regardless of where we are, say that we have, and I can't write right now, but say that we have a reaction that's losing energy, okay? And so if this reaction is losing energy, energy is traveling in this direction, right? And guys, hear this. If we have a reaction that's losing energy, energy is traveling in this direction. Is energy being gained or lost? Yes. Do you see that? Is energy being gained or lost? And the answer is yes. So in order to answer the question specifically, we need to know, are we talking about the system? Because if the system is where we are, is energy being gained or lost? Let's do it again. So energy is going this way. Is energy being gained or lost? Yes. But guys, if we then say we're going to be in the system, and if energy is going that way, is energy being gained or lost? Lost. But what if we're in the surroundings? It's being gained. You see the difference? So what we're saying, Ami, is that our frame of reference will always have us in the system. Is that okay? Why do we care? It determines the signs. You settled with that?
Yeah.
Okay. So guys, can we then agree to this? And let me zoom in. If the only way to get energy in or out of a system is through work or heat, if the system is doing work on the surroundings, the arrow, if the system is doing work on the surroundings, that's negative. If the surroundings are doing work on the system, that's positive energy change. And then here, if heat is going into the system, that's a positive change. If heat is coming out, that's a negative change. But again, guys, these positives and negatives only work if we are where? In the system. If we were in the surroundings, what would happen to the signs? They'd all switch, and that's physics. Because in physics, you always have yourself in the surroundings. In chemistry, we're always in the system. Big ideas, y'all. You okay? You sitting all right? You ready to do enthalpy?
Sure. I'm so excited.
Here comes enthalpy. Don't be scared. Okay, be a little scared. Actually, you don't have to be scared at all. So guys, ready? I'm gonna draw. This will make this better. Just a second. Boom. Okay. Here we go. So guys, again, I'm operating under the assumption that a lot of you tried to learn about enthalpy in the class notes and it kind of crashed and burned.
I just saw so many times that I was like,
Oh yeah.
what is going on?
Yeah, exactly. All right. If you focus for the next 60 seconds, you're going to understand enthalpy. You ready?
Okay.
So, guys, review. Internal energy. Two types. What do we got? What makes up internal energy?
Potential and kinetic.
Potential and kinetic. They can interconvert with no change. But now, guys, let's look at the bigger picture. How do we get energy in or out of a system? Work or heat. Guys, heat is the transfer of kinetic energy from hot to cold. It's all about vibration. So, guys, let's talk about work. Work requires what two things? Movement and resistance, right? Force of resistance. So guys, this is it. The only way to get energy in or out of a system is through work or heat. You good? Ready? Now we're going to get rid of work. We are going to assume, pretend, we are going to simplify the system. We're going to simplify the picture. And we are going to talk about pictures, about processes that can't do work. And guys, if you've got a process that can't do work, then what's the only way that the energy of the system can gain or lose if it's not work? Heat. It's heat. But we give it a new name. Guys, that's all enthalpy is.
What?
That's it.
It's just the transfer of
That's it.
energy through heat.
So guys, all enthalpy is the exchange of energy through heat when you can't do work. For some of you, it's your life story. You just get warm, but you don't get anything done.
Ouch.
I know, right? But guys, seriously, that's it. Enthalpy is the exchange of energy through heat when there's no opportunity to do work. This should bring up questions. But let's let everybody get caught up writing so we can talk about it. So guys, again, enthalpy is the exchange of heat in the absence of the opportunity to do work. Go ahead.
Does it work the opposite?
Oh, like is there a work without heat? I mean, realize I only have a bachelor's degree in chem, right? That's interesting. Not to my knowledge. But understand you're fishing in a fairly shallow puddle. So maybe, but it's not a quantity. Without getting into too much of the thermodynamics of it, I think the answer is there can't be. In order for there to be work, there has to be heat, which kind of ties into what we're about to talk about.
Becomes friction.
There's this
Yeah, kind of. I don't believe so, but I don't know. Guys, other things you want to explore relative to this idea of enthalpy? You okay? Okay. Now, the question becomes this. Is this really a thing, or is this like the land of make-believe and it's really just an oversimplification? And guys, the answer is no. We can actually get rid of work. We can create systems surrounding interactions that don't allow for work to be done. So guys, now let's ask ourselves the question, chemistry land, right? Chemical reactions. How do chemical reactions do work?
They like bubble?
They expand in volume.
Would you like to go deeper?
Sounds? The sounds?
Could be. Yeah, and so what do all of these things have in common? And guys, the answer is expansion. Sound is a great example. That when a reaction happens, it has gases, doesn't have to be gases, but it has things that are expanding that push on the air and they create sound waves. Guys, another great way to think about this is, how does your car work? You understand enough to know that you've got a cylinder with a piston, and guys, this piston compresses a gas-air mixture, the spark plug goes off, that explodes. And when it explodes, it expands, it pushes the piston down, and through a series of shafts and gears, it turns down into forward, and it moves your car. So guys, literally, that's how chemical reactions do work, is by expanding. But now guys, this, if that's true, how do we keep reactions from doing work? Go back to what work is. Think about, and you said it a minute ago, what has to be present for there to be work to be done?
Resistance and movement.
Resistance and movement. And guys, we can't get rid of the movement. Things are going to move if they want to move. So what do we get rid of? The resistance to movement. And so guys, it might be like this. You ready? If you've got gasoline and oxygen inside of the cylinder of your car and it blows up, it has to do work because there will be resistance. But guys, what if we take that same gasoline and we light it on fire in an empty beaker? Or in a beaker, I'm sorry, not empty, an uncovered beaker. Well guys, if we do that, as the gasoline burns, it's not doing work. Is it expanding? Yeah. But is there resistance to that expansion? No. Not worth talking about. And so guys, at that point, we can then say that this fire, this burning gasoline, is not doing work, not because it isn't expanding, but because there isn't resistance to the expansion. That's the difference between gasoline in your car and gasoline burning in an open container. Do you see the difference? So guys, this then becomes the important next point. Let's get rid of this. Let's get rid of this. Let's yippee skip over here. And guys, this then gets us to our conversation about enthalpy. So guys, when we talk about enthalpy, and again, this is a term. Remember how we talked about closed systems? We're also going to talk about open containers. And guys, when we talk about enthalpy, we are assuming that the reaction is taking place in what we call a constant pressure environment. We call these open containers. And guys, that is a term that you can use on the AP test. Just like closed system is officially a thought, guys, open containers are officially a thought. They're a thing. So let's dig into this a little more deeply, and then I have a question for you. And so guys, we call these things constant pressure containers, but we can call them open containers, and that's fine. You guys okay? So guys, do this with me. In your brain, think about what's going on inside the engine of your car. So we have the piston, we've got the cylinder, we've got the head, and there's that spark and an explosion. Guys, what happens to the pressure inside of that thing? Goes through the roof. And guys, that pressure is then pushing, causing the piston to go down, and we have work being done. But guys, now imagine gasoline in a beaker, and you light it. And guys, as that gasoline is burning, what happens to pressure? Nothing. In theory, if the room were perfectly sealed, that little bit of escaping gas would increase the pressure in the room, but as you said, Nathan, not appreciably, right? It's not enough to worry about. So guys, do you now picture the difference between what an open container is? Now guys, this. Imagine that we've got our burning beaker of gasoline. Open or closed container?
Open.
Open. Open or closed system?
Partially both.
It would be an open system, I think, because like all the products would be able to leave and then it surrounds.
And so now let's come back to our definition. So guys, in an open system, let's do this differently. In a closed system, what can get in and out? Energy. What can't get in and out? Matter. Law of conservation of mass. So guys, this is where this gets really weird, because when we do chemistry, we are going to understand that our chemistry is being done in closed systems that are open containers. Closed systems that are open containers. So guys, let's think about this. If it's a closed system, what can't get out? If it's a closed system, what can't get out? Matter. If it's an open container, what can't be done? Work. So guys, you ready for a really, really bad analogy?
Yeah.
Oh, good. Because that's all I've got. Imagine a balloon that can instantaneously expand or contract as the things in it are reacting. It can instantaneously expand or contract just enough to keep the pressure from changing. That's an open container in a closed system. So matter can't get in or out, but the vessel does not provide resistance, and as a result, work can't be done. Yeah.
But technically, can't the gas get out? So it's not a closed system.
In here?
It's not in the balloon, but like in an open container.
Yes, and so that's kind of, and again, crazy. So if we've got our bucket of burning gas, right? So we know that matter can get out.
Yeah.
So that's an open system. It's not a closed system. So that would be an open system, but it would also be an open container, so work can't be done, right? So when we do chemistry, we need closed systems. So matter can't get in or out, law of conservation of mass. But then we need open containers so there's no work because there's no resistance. So the stupid analogy is a balloon where the stuff can't get in or out, but the balloon expands or contracts just enough to keep the pressure from changing.
So we need to make something that can do that
Right.
in real life.
Yeah, exactly. So, but at the end of the day, the analogy is only good because it helps us understand what we're talking about. Closed system means matter can't get in or out. Open container means that there's no resistance to expansion or contraction. Is that okay?
Yeah.
Thoughts on that? You guys okay? Yeah.
She said that because the balloon expands, it's going against the resistance.
No, so the idea is that, so imagine if we put a little bit of gasoline and oxygen in here and then spark it.
Let's try
Right,
it.
it's going to go boom, it's going to blow up, right? But initially that balloon is going to try to compress it. It's going to try to keep it together. So that thing's doing work. That reaction is doing work. So that means that this is not an open container. For it to be an open container, gasoline and oxygen on the inside, spark, boom, but this balloon would go, woohoo, that stuff's inside's getting bigger, so I'm going to get bigger, and I'm not going to give resistance against that expansion.
Okay.
It's hypothetical. Is that the right
So
word?
we can't actually do
Theoretical.
this.
Theoretical, not hypothetical, theoretical. Nathaniel, go ahead.
we can't actually, is there any way that we can actually like do this, have an open system?
Yeah,
have a
and
closed
so-
system and open chaos?
Absolutely, but the thing that we actually, so the way that we get there is, again, this, it's sort of a thought problem, right? But the idea is that if we were burning gasoline in this room, in theory, if the room were sealed, the pressure in the room would go up, right? But given the expanse of the room, the functional change in pressure, we just negate. That's kind of the way we think about this.
You can do it if you interpret the system to be something more than just a bucket.
Correct. Exactly. Yep, you got it. But guys, at some point this just becomes thought problems. And thought problems you're not going to have to track down. All you need to fundamentally understand right now is that open container and closed system are not contradictory.
Okay.
Think about that. Open container and closed system are not contradictory. So closed system, matter can't get in or out, but energy can. Open container, no resistance and therefore no work. Can we all buy into those two ideas? Because guys, at this point we can then talk about enthalpy. So guys, fundamentally then, enthalpy happens in a hypothetical container which offers no resistance to expansion or contraction. As a result, no work can be done. As a result, all of the energy gain or loss is through the exchange of heat. And guys, triple dots. You know about triple dots, right? It's the abbreviation for the word therefore.
Is it the abbreviation for the one without the E or with the E?
Ooh. No, it's actually the one without, because if you wanted it to be with the one with, you'd have to put the triple dot and then the E.
Yeah.
Oh, that makes sense.
That would look really silly, so.
So instead of just
Very
using
forward.
without the E. What if you really want to use the E, bro?
You know.
All right. So guys, are you settled with these ideas? Now let's make this a little bit more applicable. So guys, when we talk then about this idea, you don't need to write this down, but we've said this, right? That the only way to change energy is through work and heat. Because if we get rid of work, we're left with heat. And what do we call heat in the absence of work? Enthalpy. Is that all coming together? Now you're not going to like this. Guys, enthalpy is heat exchanged in the absence of work. Again, heat exchanged under constant pressure. And it's abbreviated H.
Oh, come on.
Oh my goodness.
So Q is heat and enthalpy is H. But guys, the bottom line is this, and you're going to see that we will be using Q heat and H. We will be speaking of these two things at times interchangeably. You'll see that when we go to lab on Wednesday, when we pre-lab on Wednesday, we'll say things like, hey, what was the heat of reaction? But we might also say, hey, what was the enthalpy change of reaction? And at some level, we use those interchangeably. Guys, understand that when you get into college, if your professors are calorific chemists, they will not let you get away with that because they're not the same. Enthalpy is heat in the absence of work. So if your professors are really heavy into this stuff, they won't let you use enthalpy and heat interchangeably. But a lot of them will. All right, you guys good? So then this, bringing it full circle. Another equation.
That's like the same one.
It is. It's the same one, only now, guys, we're getting rid of work. So we're no longer changing the energy final minus initial. Now it's the enthalpy final minus initial. But guys, remember the idea is that enthalpy is just heat in the absence of work. So guys, the idea then becomes this. If the change in enthalpy is positive, that's endothermic. Because guys, endothermic does not refer to work, it refers only to heat. And when heat is in the absence of work, it's enthalpy. So guys, the technical definition for enthalpy is a positive delta H value. This takes in heat. And then guys, similarly, a negative delta H value heat is being given off.
Enthalpy makes like twice as much sense now.
See?
All of the chapters where, all of the sections where it's like,
Oh, yeah.
enthalpy of bonds.
Right?
What?
Yeah.
Now I actually get it.
Well, you see, if it made 0 sense, it could twice as much sense because then it's still.
Okay, so it made a tiny little bit of sense. So now it makes just like.
But you understand
we did
it.
addition, not multiplication.
At some level, you're having a college
We
moment.
now understand.
Yeah. But realize this. Hard to learn from a book. Don't mean this, I'm not bragging. Hard to learn from a book. Easy to learn from a good teacher. The problem is that in college, sometimes you lose those good teachers. My daughter was a camp counselor this summer, and one of her friends from camp is actually a nursing student up at Weber State who's taking chemistry. And she called me and she's like, hey, could you help? She needed help with density calculations. And I'm like, how are you not understanding this? And she's like, my professor's from India and I can't even understand what she's saying.
Sounds funny.
Yeah, it happens.
That's why we take chemistry again.
That's actually why, while you're in high school, you're going to go around to all of your good high school teachers and tell them thank you. Because high school has a higher concentration of really good teachers than any university on the planet. Yeah. All right. So guys, watch this. This is where we're going to wrap up the day. Ready? So we've now tied this to endo and exothermic, and we're thinking final minus initial, right? Yes. Because change is always final minus initial. But now, guys, this. Now let's talk about chemical reactions. What do reactions finally make? Products. What do reactions initially start with? Reactants. Does this make sense?
Yes.
Write it down.
I understand now. That was in the notes too.
So guys, when we talk about these ideas through the lens of chemistry, what we're going to be talking about are actually not final minus initial. We're going to go products minus reactants. Because products are where a reaction ends up, finally, and reactants are where a reaction initially starts. Now guys, this leads us to the idea of what are called thermochemical equations. This is going to take us 2 days to cover well. Because we are going to be doing thermochemical equations for the next 2 days. When we do it on Wednesday, we're going to talk about them experimentally. When we do them on Friday, we're going to do them computationally. We're doing experimental first because it's the lab we're going to do.
I just have a question about enthalpy, if that's okay. I know we kind of moved.
Yeah,
past
no,
it.
go, yeah.
We're kind of
Yeah, no.
So does an explosion
Yep.
in a combustion engine, for example?
It's contained.
Yeah. Does it produce less heat the more pressure is put on it?
Say that
It
again.
has to do more work.
If
Does
it's
it-
doing more work to move a piston the same amount, is the reaction producing less heat?
Yes.
Okay.
Yeah.
So
yeah.
like if I stuck my hand into burning gasoline, well, actually it's not really a one-to-one comparison.
Let's see.
Potentially it could be hotter.
Keep an eye on him.
Consider not.
But the same amount of gasoline being burned with the same amount of energy being put into it
Yeah.
would burn hotter under constant pressure than in an engine.
It would burn hotter.
So let's
It would give off more heat.
Let's talk about extremes.
Okay.
So when gasoline burns, it has an amount of energy that it will release.
Mhm.
If any of that energy goes to work, it will not go to heat. And so what you're saying is true, that the less resistance and therefore the less work, the more heat that comes out of it. Okay? But now did that make sense, y'all? But now I'm going to plant a little chapter 19 flag with you. So instead of burning gasoline, let's burn coal. And where were we burning coal in the late 1800s? In trains. And so what they were finding was they knew how much energy should be coming out of this burning coal. But what they were finding is that energy was not going to move the train. It was inefficient. And so some chemists started toying with this, and what they found is that all of the energy wasn't just going into moving the train or heating the train up. Energy was being lost somewhere else. And the answer we find out is entropy, disorder. That's actually the problem that led us to figuring out about entropy. A guy named Gibbs did it by studying trains, locomotives.
Do you guys learn about this in this class, or is it a different class that I learned about this in?
It will be. It's chapter 19, so we're going to get there in a couple days. Actually, next week we'll start talking about.
Oh, we
this.
haven't yet.
We have not yet. Yeah. So it could have been physics.
I think it was more recent than that. I'll figure it out. It's not
Okay.
important.
Yeah, but you're right on it. You guys okay right now? Okay. So now do this with me, guys. Thermochemical equations. What are thermochemical equations? And guys, this is an example of a thermochemical equation. So let me give you a second to sort of fiddle with this. (2H2 plus O2 yields 2H2O, and then delta H, negative 4 negative 483.6 kilojoules. So guys, we are going to spend we're going to spend the next 10 minutes, and we're just going to dig into this equation. Because guys, there's so much rich information right here that we've got to dig into this. You ready? Question number 1 is this. What does it mean that the delta H value is negative? What is happening to the, and so let's define our system. Guys, our system is the hydrogen and oxygen atoms that are involved in this reaction. That's our system. So guys, if that's our system, what is happening to the energy of our system in this reaction? Energy is going down. That's what the negative sign means. Guys, that means that this reaction is endo or exothermic? Exothermic. Now guys, the question is this. Where is that energy coming from?
The formation of bonds.
Yeah. Guys, if you want to draw this. So guys, here's what we've got. We have got 2 diatomic hydrogen molecules. And leaving off valence electrons. I'll draw it vertically. I hope that's okay. We have 1 diatomic oxygen atom. And then, guys, in our products, we have, and again, I'm being sloppy with valence electrons. In our products, guys, we have 2 water molecules. Now, when this reaction takes place, let's just call that 500. Guys, 500 kilojoules of energy comes out of this reaction. Where does that energy come from? The formation of those 4 bonds. As oxygen bonds to hydrogens, twice in each molecule, guys, that's where the energy comes from. But guess what? The formation of these 4 bonds does not release that much energy. It releases more.
But we use up some energy breaking the bond.
Yes. So guys, these bonds have got to break. And guys, that provides the net accounting of all of these energies. And this is what we're going to be doing on Friday. We're going to look up how much energy does it take to break the bond in hydrogen, times 2. How much energy does it take to break the double bond in oxygen? We're going to add those numbers up. Then we're going to add up how much energy is released when oxygen and hydrogen bond together, times 4. And guys, what you're going to find is that there's more energy released than taken in, and that amount of energy is this amount of energy. Guys, there's a name for it. It's called Hess's Law. Remember reading about that in chapter 5? That's what Hess's Law is all about. You okay on the idea? Go ahead.
So this reaction is literally just burning hydrogen.
Yeah.
and oxygen.
Yeah, it's
and that's why that's something hot.
Yeah, and it's giving off heat. Absolutely. And that's exactly. Go ahead.
It's probably not a super smart question, but is this still a combustion reaction?
It is, no, so technically it's not. Because remember, combustion involves a hydrocarbon and oxygen producing carbon dioxide and water. But the same thing would be true. If it was combustion, it would be the breaking of the hydrocarbon, the breaking of the oxygen, and then the formation of the carbon dioxide and water. But you know energy is given off, right? Which means the energy released by bond formation is greater than the energy taken in breaking down the reactants. And we'll actually look at that in diagram form. It's really interesting. Yeah.
So what determines like how much energy each bond requires to break?
Right? That's sort of the holy grail, right? And there's so much that plays into this. It's electron structure. It's electronegativity. It's actually, when we say electron structure, not only valence structure, it's also core electron structure. And we're going to talk about that more in chapter 6. When we start talking about what is called effective nuclear charge, which is actually the charge of the nucleus minus shielding. We're going to get into all of that stuff later, but all of those things play a part. You buy it?
Yeah.
Okay. You guys good?
On that for now.
Okay, now I have another question for you. How much? We're calling that number 500. Guys, how much hydrogen has to burn in order for it to give off, again, 500 kilojoules of energy? How much has to burn? 2 moles. So guys, the energies for these are as written. So you burn 2 moles of hydrogen in the presence of 1 mole of oxygen, and you get out 2 moles of water. That will release 500 kilojoules of energy. Good? What if it's 4 and 2 and 4? Then you double it. Guys, what about this? What if we flip the arrow over, and what if we make this a decomposition reaction rather than a synthesis reaction? Then you just flip the sign. Does that all make sense? Because guys, all of that is contained in these ideas. So guys, it goes like this. First of all, enthalpy is an extensive property, which means the more of it there is, the more of it there is. So if you're burning more, in this case hydrogen, you're going to get more energy, unlike density. You can have a drop of water or a lake full of water, the density is the same. Then guys, these, as we said, these are given for the moles represented. They can be reversible. You switch the sign. And then guys, you're going to see that enthalpy can be phase dependent. And we'll talk more about that in the coming days.
I wrote down something about that.
Yeah, and so fundamentally the idea is this. If this reaction forms steam, the amount of energy that's given off would actually be less.
That's because you have to boil water.
Yeah, exactly. Precisely. You got it.
Enough energies.
Yep. Yeah, you got it. Yep. You guys okay on those ideas? We're done. Let you catch up. You guys all okay? No? Ken, how you doing? You look like you should be on your couch watching a movie. You guys good? Okay, so guys, this then is your homework. This is going to freak out. Just relax.